Hello and good morning, everybody. Welcome to our Embedded World seminar. This is on building safer, efficient, and intelligent autonomous robots with sensing and processing technologies by Texas Instruments. Our presenters today are Manisha Agarwal and Jitin George, product marketing engineers for the technology that you'll be seeing. My name is Sam Vasali, and I'll be one of the moderators today. Just a reminder, all attendees' microphones are muted, but if you have questions, please post them in the chat addressed to everyone, and we will be answering them throughout the session. And if we have time at the end of the session, we may also answer some over the meeting. With that, I will hand it over to Manisha and Jitin.
Thanks, Sam. Welcome, everyone. My name is Manisha Agarwal. As Sam mentioned, I'm a product marketing engineer with Jacinto Processors business in Texas Instruments and responsible for all edge AI applications, including robotics. In this presentation today, I will cover introduction of autonomous robots, functional safety for robotics, TI technologies serving autonomous robots. Followed by that, Jitin will cover challenges with AMR sensing needs and will introduce the differentiation that TI mmWave sensors bring to the AMR sensing suite. And after that, I will introduce Jacinto processors for accelerated vision and sensor fusion for safe and efficient robots. An autonomous robot is any robot that can navigate in an unstructured environment with a higher level understanding. While it is relatively young technology, they have already branched off into a number of distinct varieties in factories, warehouses, cities, and homes, helping ease human life. So an autonomy requires that the robots are able to sense the environment, perceive the environment, to localize itself in the map, and dynamically detect the obstacles around, track them, plan the route to reach the goal, and control the vehicle to follow that plan. And act only when it is safe to do so, avoiding situations that pose a risk to human safety, property, or the autonomous system itself. So as these robots are working in closer proximity to humans than ever before, the need for them to be not only autonomous, mobile, intelligent, and energy efficient, but functionally safe is critically important. And that's where TI products ranging from sensing, processing, and control need help system integrators meet the rigorous requirement of functional safety standards, such as ISO 26262 and IEC 61508. Our technology suite ranges from the sensing, processing, all the way to acting, and mentioned with the product names I'm showing here on the screen. So Texas Instruments has been developing processors for functional safety in industrial and automotive applications for years with products such as our Hercules microcontroller line or TDA automotive processors. We have worked with industry-leading safety experts to develop the internal processes necessary to achieve the highest safety integrity levels for systematic faults and have developed the types of features, diagnostics, and tools necessary to help system integrators implement all sorts of safety applications. TI's expertise extends beyond the processors we'll be talking about here today to include power, analog, and signal chain components to enable functionally safe systems. We have leveraged this expertise to bake in safety from the ground up on the new families of radar and processors we will be discussing today. With this, I hand over the presentation to Jitin to talk about the TI Technologies sensors offering to the autonomous mobile robots.
Thanks, Manisha. My name is Jitin George, and I'm a product marketing engineer with the industrial millimeter wave team here at Texas Instruments. And I'm mainly responsible for factory automation and robotics. Now, before I get into the details of sensing with millimeter wave, let's talk about why sensors are so important in robotics. All right, let me use a simple analogy here. Just think of us humans. We humans have 5 basic senses, right? Sight, hearing, touch, smell, and taste. Now, what would happen if, say, you were to lose 3 of those 5 senses? Let's say you're walking down the street, or let's take an example of a factory floor. Right? You're walking down and you've lost your sense of sight, hearing, and touch. At some point, as you can imagine, right, you will crash into something. And the same really applies to robots. A robot without sensors will inevitably crash into obstacles. It could crash into walls, other robots, and even humans. And this could result in serious injury. And this is really why sensing in robotics is so important. Now, excuse me, when it comes to these autonomous mobile robots, or AMRs, there's really 3 key challenges that need to be solved. Safe human presence detection, mapping and localization, and collision avoidance. So let's talk about these. So safe human presence detection. So here, basically what we're doing is you want to create a safety area, or what I like to call a safety bubble around the robot. And you can see that here, right, with the yellow and the red zones around the robot. And basically what it's doing is, it's going to trigger the robot to slow down and stop when a human is detected within these zones. Next is mapping and localization. Again, very important because the robot needs to, first of all, know the map of the environment that it's going to operate in. Is this an indoor environment? Is this outdoor? Right? You really want the robot to know where it is, because at some point it will need to go back to its initial position, either to charge or to pick another object, whatever it may be. And then finally, you have collision avoidance, where you want the robot to not only avoid humans, but also the objects that are in its way, and basically navigate around them. And if you look at the slide, right, you can see there are several different types of sensors that can be used to solve these challenges. What I want to do is really drill a little deeper into radar, and I want to show you how our TI millimeter wave radar sensors can enable you to solve some of these challenges for AMRs. All right, so let's talk about radar. Just a little bit of background for those of you that are new to this. Millimeter wave, by definition, is a high frequency band between 30 and 300 gigahertz. And what really sets millimeter wave radar apart is the ability to provide the range, velocity, and angle of arrival information of multiple objects in the scene using a single sensor. Now, when you think of radar in robotics, it might be somewhat of a new concept to at least some of you. But if you look at the automotive, radar has been around for a while. In fact, auto radar is one of the key components of advanced driver assistance systems, or ADAS, and has been used to monitor surroundings of a vehicle for driver assistance. So what we're doing here is taking some of those same ADAS concepts from automotive, like surround view monitoring, like collision avoidance, for instance, and we're bringing that to robotics. So how are we doing that? We already talked about collision avoidance in the previous slide, right? This was one of the key sensing challenges for AMRs that we talked about. What's critical here is that the sensor detects any obstacles that might be in the way, and then triggers the robot to take action so it can navigate around those obstacles. From a millimeter wave perspective, 3D presence detection capability of our sensors enable you to do just that, where the position and velocity information of people and other objects in the scene is used to trigger the appropriate robot response. When it comes to safety and presence detection, TI millimeter wave radar sensors can create these surround view slowdown and stop zone, which enables the robot to detect and react to the environment. And depending on the position, the speed and trajectory of the person, the robot can make the decision whether it can safely continue on its path, if it needs to slow down, or even stop completely. So this is another challenge that TI millimeter wave can solve. And there are several other benefits to using millimeter wave radar in your robotics application too, right? First would be functional safety. We already talked about this, right? Robots these days work alongside humans, so it's critical to ensure human safety. Robot developers want to design systems that are functionally safe, that can detect and prevent, or at a minimum, detect and reduce the impact of dangerous failures. Right? We at TI understand this, and we are making the investment to get our millimeter wave devices certified up to SOC 2. We also have additional documentation, additional resources, and collateral such as functional safety manuals, FMEDAs, and software diagnostic libraries. And this can help you really streamline the certification process for your system. Outside of safety, you can ensure reliable detection of glass and other transparent material with our millimeter wave sensors. Other sensors like LiDAR, for instance, would have a challenge with this because they typically tend to see through the glass. Radar also has a big advantage when it comes to added robustness in challenging environmental conditions. Radar, as you know, uses radio waves instead of light to detect objects. So it works really well in rain, fog, and snow. So for outdoor use cases and even for indoor use cases, right, in the presence of debris and smoke, where optical sensing technologies like cameras do tend to suffer. What I want to do now is talk through a couple of our demos to show you how we've solved some of these challenges with radar. All right, so I want to start here with the sense and avoid demo, and this is mainly for collision avoidance. In this case, we have a single millimeter wave sensor that we've mounted on the front of the robot. The evaluation module, or the EVM, that we've used here is the 60 gigahertz IWR 6843 ISK. This provides 120-degree horizontal field of view, 30-degree vertical field of view, and the demo has been set up for a detection range up to 10 meters. But again, this can be configured depending on your requirements. Keep in mind, from a sensor standpoint, TI millimeter wave can support ranges way beyond 10 meters. But again, for the purpose of this demo, we've kept this to 10. What's great here is that we've done all of this within the ROS environment. ROS, again, as some of you may already know, stands for Robot Operating System. It's open source. It's used by several robotics developers, language agnostic, and really gives you a lot of flexibility and enables you to easily take our millimeter wave sensors and then test the functionality and performance in your application. So what I want to do is really show you how this demo performs and what were some of the things that we showed with this demo. So the images that you see on the right are actually screenshots from the actual demo in action. And here, as you can see, right, we placed several different types of objects in the scene. We have dark objects, cardboard boxes, glass, and even transparent material. Our millimeter wave sensor was able to reliably detect all of these objects, enabling the robot to easily navigate around them. What we did then was we took this one step further, and we wanted to showcase our performance in complete darkness. And our sensor performance really was unaffected. It was still able to detect all of the same objects without really colliding into anything. And this is, you can see the screenshot here on the very right, but we actually have a demo for this. We actually have a video for this demo. It's available on TI.com, and I've actually added the link here on the top left. So please do check it out. I also want to point out that we have a lab available for this, and it's available on TI Resource Explorer portal. And this provides step-by-step instructions with the reference software. And this can enable you to run this demo and evaluate the performance of our sensors for your application. The link to this lab and also other relevant links have been provided here on the bottom right of your screen, and this can help you get started with this demo. All right, so now let's talk about the next demo here. This is our 360-degree safety bubble demo. Here also we've used the IWR6843 ISK EDM, and we have 4 of these mounted around the robot. And we use 4 sensors here to cover the full 360 degrees around the robot for surround view monitoring. Detection range, again, for this demo has been set to 10 meters by default. But as I mentioned in the previous slide, right, this is configurable to suit your end application needs. This demo is mainly targeted for safe human presence detection in AMRs. So the IWR6843 sensors that we used here, they create these precise warning and danger zones around the robot. So if a person were to be detected within that warning zone, the radar sensors would trigger the robot to start slowing down, and then eventually bring it to a stop as soon as the person is within that danger zone. Again, the parameters here for the warning zone and danger zones have been set to 2 meters and 1 meter respectively, but again, these parameters are also configurable. Now, again, going back to what this demo is able to do and what we've tried to showcase here, let's take a look at the images on the right. I want to focus specifically on the unconscious human use case here. As you can see, there's several different objects in the scene here. You have the forklift, the trash can, also this trash compactor. And even with so many things around, you really want the sensor to detect this unconscious person on the ground. So it can then trigger the robot to stop right before it gets too close. And the millimeter wave sensor does just that. If you look at the point cloud visualization here in the image, you can see, right, all of these objects, including the human, is detected by the sensor. And as soon as the person is within the yellow zone, the robot starts slowing down and then comes to a stop when he's within that danger zone. We've tested several other use cases as well for this demo. The other example here that I've shown here is with a person walking into the path of the robot with a pallet jack. So all of these use cases and several more have been tested. We've captured all of this in a video. This video is available on TIA.com. I've added the link here on the top left, but I do want to call out this demo is one of the demos that we are showcasing here at Embedded World. So please do check it out when you get a chance today. We do have a lab available for this demo as well. Everything, again, has been done in ROS, so you can easily run this demo, evaluate performance of millimeter wave in your application. And as I mentioned before, right, all of the links to the lab and also other relevant links are provided here on the bottom right. Just one last point I want to make here. I've talked about some of these parameters being configurable, parameters such as the range and also the slowdown and stop zone radiuses. So if you want to configure any of those parameters, instructions to do this have been captured in the 360 Safety Bubble Lab FAQ link. And again, this is provided here as well. All right, let's move on here. So we've talked about radar. We've talked about the various advantages of millimeter wave when it comes to robotics. And we also looked at specific AMR challenges that radar can solve. So at the end of the day, you might be wondering, right, is radar all I need to solve all of my AMR sensing problems? And the answer isn't really very straightforward. It really depends. There might be some use cases where radar can solve most of the sensing challenges, but for the more complex AMR applications, a single sensor alone might not be sufficient, but might not be enough, no matter what type of sensor you're using. So let me go back to the human analogy I used earlier. Our sense of sight helps us see everything that's around us, right? It helps us easily go from place to place, walk around freely without the fear of colliding into something. But what if now you were trying to make your way around a completely dark area where you're not able to see anything? It's going to be difficult, right? Same thing with sensors. These sensors have their own pros and cons. So let's take a look at this table here. And let's focus on radar and cameras for now. What are some of the strengths of radar from this table? And these are highlighted in green, right? Radar can enable good object detection capability. They can provide range and velocity information of objects at the scene. And radar is also immune to environmental factors like poor lighting. So, their performance remains unaffected even in the most challenging environmental conditions. Now, on the flip side, they do have limitations when it comes to object classification and the ability to precisely detect edges of an object. Now, when you look at cameras, on the other hand, some of these limitations that you had with radar are the areas of strength for cameras, right? They provide great object detection capability, object classification capability. And they can also be used to precisely detect edges of an object. But again, downside for cameras, they aren't very reliable in poor lighting conditions, or for indoor environments, even smoky, dusty conditions that are prevalent in factory settings. Ultimately, if you look at the last column in the table here, you want sensors like cameras and radar to complement each other. And you really want to leverage the strengths of each of these sensing modalities through sensor fusion to solve some of these more complex AMR sensing challenges. With that, what I'm going to do here is I'll hand it back to Manisha, and she'll go into a little more details into this, and she'll talk through how you can accelerate vision plus radar sensor fusion with TI Jacinto 7 processors.
Thanks, Jitin. So as Jitin mentioned, vision sensors bring a lot of strength to the table as its perception very close to a human vision system. So the benefit that vision sensor provide to the table to solve this challenging problem of localization and obstacle detection and avoidance are that they have high resolution spatial coverage, and they have the ability to not only detect the objects, extract the features from it, but also classify them. And again, your advancement in the vision-based deep neural network technology makes it possible to solve such complex problems more innovatively using neural network methods. And one of the biggest benefits it brings to the table is that they are cost efficient compared to other sensors like LiDAR. But the downside of the vision sensing is that they are very computation intensive. And as these robots are energy constrained and CPUs and the GPUs are power hungry, desire is to keep the CPU or the GPU-based processing to minimum for an energy efficient, robots, and at the same time they be safe. So that's where we introduce you the TI's Jacinto 7 platform. It's a highly integrated, scalable family of processors, purpose-built for smart, safe, energy efficient, and cost-effective edge applications. So for typical vision processing and sensor fusion types applications. So in a typical architecture, application processors comprise of a CPU and a GPU for compute, and then rest all other components such as the ISP, disparity, MCU, PCI Ethernet switches. They're all external to the processor, making it complex and unoptimized for system and cost. So in Jacinto 7 TDA4X devices, we integrated all these components in one single SoC, along with class-leading deep learning accelerator, powerful computer vision accelerators, and while doing all these, designing the SoCs bottoms up, keeping the functional safety in mind. So, here I'm showing on my screen how a typical, an architecture or often efficient vision plus sensor fusion-based robot looks like. So our first processor in the family, TDA4VMIT architecture or the capabilities is what I'm going to show in the screen. So what here we have is this entire processing on the main domain FIL2 capable and the computation intensive task of the vision and the deep learning processing can happen on the accelerators at low power and low latency. So we have here vision accelerators. That includes, your image signal processors and the image rectification, accelerator for image rectification, as well as multi-scaling. These all can happen for multi-cameras simultaneously, such as, you can bring 8 2-megapixel resolution cameras or 2 8-megapixel resolution cameras and achieve these tasks at low power and low latency. On top of that, the device has accelerated depth and motion accelerators. So you can now detect this depth through the stereo sensors, estimate the depth to the stereo sensors, or you can do the dense optical flow on multiple cameras again up to 2 megapixel resolutions. With the computer vision, you can also add on to it a deep learning processing with our class-leading neural network accelerators. On this first device, we have it running at 8 TOPS. And again, the differentiation here it brings high throughput and low latency to the processing. Further, you can do your low power processing on TI DSPs by doing the processing on the images, or running the key task of the localizations, or doing the FFTs on the radar sensors. So all these are very computation-intensive tasks, which happens very efficiently on TI GDDR4X processors. Now you can just leave your higher-level processing tasks such as mapping, planning, sensor fusion, tracking, etc., on your Cortex-A core. Now, to make it robust and safe for the environment, we have here integrated the Lockstep R5 and a safe island, a fully isolated power and the freedom from interference isolated and MCU domain, which is SIL3 capable. So now you can achieve the robustness through the redundancy, not only on the computer vision and the deep learning side, but also redundancy through the Lockstep R5 processing. On top of that, in this processor, we have integrated high-speed interfaces to bring multiple cameras into the device. So we have 2 CSI-2 ports, which can bring in up to 32 virtual channels. There are multiple USB ports, as well as integrated 8-port Ethernet switches and PCI switches to bring your different sensing modalities, as well as connecting the devices for multi-chip architecture. So what do we have here? With this high level of integration, with the combined neural network processing as well as the accelerated CV, you can solve your localization and the obstacle detection problem in a hybrid fashion for an energy efficient implementation. And both of those processing can happen either for mono camera or for the stereo camera. Now, to add on top of that, you can add more sensors such as radar, LiDAR, and utilize the robustness through the redundancy on the sensing and robustness through the redundancy on the processing, as well as with the SIL2 and the SIL3 compliant SoC, you get really a very safe implementation of the robot while it is being smart, but also energy efficient and cost effective, because we have integrated all the functionalities into one single SoC. So what about programming of such devices? So while it has a lot of accelerators, how do we go about programming the device? So at TI, what we have done is we have taken an open source approach, and we have adopted a software architecture where we give you programming experience of CPU and brings the system benefits of specialized accelerators. So programming of the neural network accelerators, we have embraced and adopted the 3 open source runtime engines, TensorFlow Lite, TVM, and Onyx Runtime. So depending on your needs, which framework you are using, which of your models are enabled by one of these runtime engines, you have the flexibility to pick your favorite open source runtime and accelerate those models onto TI processor accelerator, just staying at a Linux user space with your favorite Python or C++ based APIs. We have scaled business not only to the deep neural network accelerators, but programming of rest of the accelerators is also enabled through the user space, Linux user space, via the middleware framework such as OpenVX. And going forward, we are also enabling it through GStreamer. We integrate computer vision as well in our processor SDK package, and all the foundational components, which is your drivers for various peripherals and interfaces running in the Linux environment, or the multimedia processing, and the vision libraries for all the vision accelerators that I had showed earlier, along with the hand-optimized deep learning library. They are all part of our foundational components with a production quality software that is packaged in the SDK. So now to ease further, the developer's task, as Jitin was also mentioning, that ROS is very popular in the robotics environment, in the robotics world. So we enable all these through the ROS environment with the full stack to ease the developer's experience on TI processors. So here, we have several out-of-box applications integrated into the SDK today. This includes, the signal chain pipeline for the stereo disparity estimation using our accelerators, or fusing it with deep learning to do a 3D obstacle detection, or, energy efficient visual localization, or processing multiple cameras. So here we have, shown a demo of 8 2-megapixel resolution camera at 30 FPS. All of these processing happening on one single SoC. And then we have several examples of the hardware-accelerated image classification, object detection, semantic segmentation, and simultaneous execution of multiple of such models on our neural network accelerators, demonstrated in the SDK. So here specifically, I wanted to talk about two of the demos, which we already mentioned. They are very critical for the safe operation of the robot, as well as their intelligence. So one of them is the localization demo. Here, we have demonstrating the localization demo implementation on TI TDA4X processor based on the hybrid perception, which is utilizing both deep learning and computer vision. So in typical world, these are done on, the CPUs and or GPUs. They are very, resource consuming, as well as, they consume a lot of power to process it. So here, the feature detector and the descriptors are solved through the deep neural network base. So it's inspired from the Kazi. It's a TI design architecture where, the feature descriptors are through the neural network accelerators, and the rest of the processing, which is thresholding or the upsampling, plus sparse convolution or 2D to 3D matching, and the post estimation, post filtering, they all happen efficiently on TI DSPs. And these processing on the TI DSP, they are available to our customers to use it in their implementation of the localization demo. So here on the right side of the left side of the screen, I'm showing the resource utilization for such complex processing for a mono camera of 768 x 384 resolution running at 30 FPS. So we can see that Cortex-A72 core is totally free, and there is minor load on our deep neural network accelerator, which is C7X plus MMA. And the TI 6th generation DSP-C6 is utilized 45% to do all the post-processing job here of the localization. And the DDR bandwidth is utilized only 8% because of the efficiency or the innovations that gone into the architecture, where we have large internal memory and a high bandwidth bus infrastructure, along with the data being passed to the computation unit without being stored by the caches. So with all these efficient architecture and the software implementation, we see that such complex processing can be solved so energy efficiently on TI processor. The other demo that I wanted to talk about is the 3D obstacle detection demo. Again, same is being solved for the for vision sensors with the accelerated deep learning as well as the computer vision. So here I'm showing a demo where we utilize the stereo camera from the Z stereo camera. The inputs are coming from them, and then all the processing, which is your stereo rectification, your disparity estimation, or the disparity refinement, they happens in our hardware accelerator or the DSP. And there is an example of it in our SDK, which shows this baked pipeline that you can utilize for your own cameras. One of the image goes to the deep neural network accelerator for semantic segmentation. Then these computer vision and the deep learning outputs are fused together to generate an egocentric occupancy grid map to create a safety hazard detection bubble. So fuse the deep learning and the conventional stereo vision for the robust 3D object detection. So we have this demo, again, posted in the Embedded World site, and I would like to show the demo here again. Thank you for showing the recording video. So all these software and the demos that I showed here are packaged in our Processor SDK, which is a unified software platform. This not only unifies all the processors in the Jacinto portfolio, but also unifies the software from our Satara product line. So it is built on a common foundation of drivers, frameworks, libraries, codecs, and development tool, and utilizes the best mainline Linux support. And we update our SDK every quarter, where our customers can get the support NRE free and royalty free on e2e.ti.com. Here I'm sharing on my screen links that you can check out if you to develop your robotics applications with TI today. So both for the TDA4 VMID and millimeter wave radar, the links are shown for you to get started. And there are several other links for the different products for the action side that I mentioned earlier, which comes from our Satara, Jacinto, and the MCU product line that you can check out in the PDF version of this slide. With this, I conclude this presentation. Thank you, everyone, for your time today.
Thank you, Manisha. Thank you, Jitin, for the presentation. I'd like to thank everybody for joining us. I'll remind you that all sessions and recordings and presentations from TI will be available on ti.com/EW. You'll also receive an email with links to on-demand presentation and post-event survey. Thank you so much for our presenters today and everybody who participated in the panel. Have a good day.